Okay, folks, so we're talking about our murder mystery time of death right now. And so the first thing we did was we went ahead and read through the memo to the investigators because police are investigating a mysterious death at a local hotel, and they would like your help in figuring out the time of death. So the elevator operator at the Ritz Palace Hotel, his name is Alex Moore, right there, died from a stab wound while on duty last Thursday evening. His body was discovered by a family on its way down to the pool. When we arrived at the scene, we canvassed the area, we found nothing. The elevator is full of fingerprints of hundreds of different guests who ride in the elevator during the day. We have several suspects, but we're having trouble pinning down time of death. If we can determine that, we have a good shot at finding the killer. And then the note from the coroner tells us that the body was found at 9:45 a.m. The body's temperature was 78.8 degrees Fahrenheit or 26 degrees Celsius, and the elevator temperature was 68 degrees Fahrenheit or 20 degrees Celsius. So one of the methods that we use to determine time of death is called algor mortis. It's the cooling of the body after death. And basically the body will cool until it reaches the temperature of the environment in which it is in. So that leads us over here to setting up our lab. So the first thing we want to know is to determine how body size affects cooling rates, we are going to measure the differential cooling of a large body and a small body, which you can see here in the picture. So the idea is that you are now going to give us a prediction. What do you think is going to happen? Which is going to cool faster, the large body or the small body? And that's what you put here. And then I need an explanation of why you think that's going to happen. Do you think the large body will cool faster because it has more surface area exposed to air? Or what do you think is going to go on? So that's what we're looking for on this one, is for you to make a prediction. Then we're going to set up the lab, which we're actually kind of running as a demo because the software doesn't work on your Chromebooks. And that gets us over here. We're now collecting data. As we're collecting data, you are going to be watching this video right there. And that would get you down here so you can answer all of these questions as you go. And all of these questions down here to the bottom, where we are now going to hit statistics and look at the statistics for our temperature. So I'm looking at the graph, and the large body has a maximum of 47.37. So 47.37, decimal point right there. And the small one has a maximum of 47.12. 47.12, which then takes us over to our minimums. So it started at the minimum, so where it ended was 45.19 for the large bottle, 45.19. And for the small bottle, it ended at 42.44. So 42.44. Wrote that in the wrong spot. So get rid of that. Now we have to figure out the differences in those. So if we go ahead and do our math, we can take our amounts and subtract them. So I'm going to come back over here. It was 47.37, so we'll start with 47.37. Whoops. 37. And we're going to subtract 45.19. And that's going to give us this number, which is going to go right there. We do the same thing for the small bottle. Then you're going to answer which bottle do you think cooled the most, and then they have a rate. Well, we did this over 20 minutes. So the change in temperature, here, let me get this, change in temp divided by 20 minutes will give you the rate degrees per minute, so that it will give you the rate there. And then you do that for both, and then you figure out which one had the faster rate of cooling, because the faster rate of cooling may not be the one that's the coolest at the end. Depends on where it starts, right? So then you need to refer to the case report all the way back on the front page and see what was the body's temperature on the case report on the front. So if we go back to the beginning, here we can see the body's temperature was 78.8 degrees Fahrenheit. So we can enter 78.8 degrees Fahrenheit. The time the temperature recorded was 9:45 a.m. and the elevator temperature was 68 degrees Fahrenheit. So then we're going to move that forward and use the Gleister equation. Here, 98.4, subtract out the temperature of the body, and then divide the whole thing by 1.5. So that means 98.4, because that is the constant, and we're going to subtract out our temperature, which was 78.8. We're going to get some sort of a number, right? And then we're going to divide that number by 1.5. And that should give us the PMI, or hours since death. Post-mortem interval is also right there. Then you should be able to count backwards on the clock and see when approximately he died. So there you go. That's a basic introduction of how this works.